All right, so we were speaking about the binomial and hypergeometric random variables, and here I would like to say a few more about the connections between binomial and hypergeometric. Remember, the very first thing is that binomial, you have n trials, and each trial is success or failure independently of the next trial, which is identically likely to be success or failure. With hypergeometric, what happens is that if you get a success on first trial, that influences your likelihood of getting a success on the next trial because it's sampling without replacement. Yes? All right, so that was the first connection. Here is one other connection here. So let's suppose we have this Fischer exact test. Researcher wishes to investigate whether a certain disease is more prevalent among men than among women. A random sample of n women and m men is gathered, and each person is tested for the disease. So we will let x denote the number of women who have the disease, and y be the number of men that have this disease. So do you agree that each of those are binomial random variables? Assuming that, I mean, because we have, although you might say, all right, so we imagine that each woman is a trial, right? So we have how many of them? We have n women. So each of the n women is like an independent trial, and because the population is large, we approximate it by the idea that if we find that one woman has this disease, this does not affect the outcome for the next person. Yes? And y is the number of men that have this disease. So x is a binomial random variable with some parameter. Maybe a woman and a man are not as likely to have the same disease. For example, color blindness. Does anyone know anyone who is colorblind? My brother is, for example. So color blindness is more prevalent among men, as other diseases are more prevalent among men, and some others perhaps among women. So there is no reason to assume that men and women have the same likelihood, but we would imagine that x is a binomial random variable with parameters n and p1, and y is a binomial random variable with parameters m and p2, where p1 and p2 are not known because we do not know how prevalent is this disease in the general population. Okay, and then we can make the null assumption, the null hypothesis, that there is no difference between p1 and p2, right? In other words, initially there is no reason to suppose that women and men differ on their likelihood of being afflicted with this illness. And then the question is this null hypothesis likely? Okay. In other words, maybe this is true and maybe it's not true, and we will try to verify whether this null hypothesis is likely. So far, everyone understands? Yes, I'm asking because I'm just reading it now. I didn't know what I'm going to do today, so I'm asking, of course, if you understand and if I understand. Okay, so then what you have is we have this table, right? Suppose that what happened is written in this table. So we have women, there are k women and that have the disease, and n minus k women that don't have the disease. Naturally, the total has to be n. For the men, you have, so total people that you discover that have the diseases are people have this disease. You understand? So I tested both women and men, and R of them have the disease. And what you have is k of them are women, R minus k of them are men. So far good? Then the rest of the population, n plus m minus r, they mean the sample population, do not have the disease. So we have n minus k women don't have the disease, and m minus r minus k, don't have the disease among men. Good. So then notice that the probability that x equals to k, given that the sum is equal to r, is by conditional probability is the same as probability x equal to k and y equals to r minus k, right? Because if x is k and x plus y is r, y must be r minus k. So I just take the intersection here, right? X equal to k and x plus y equal to r. I can write the intersection as x equal to k and y equal to r minus k. And then here I divide by the probability that x plus r plus y equals to r. So the sum x plus y, if it's true that the null hypothesis works, x plus y is a binomial with n plus m trials and probability of success, probability of having the disease being p. Good. Thus, the probability that x equal to k, given that x plus y equal to r, is going to be n choose k times the probability pk times 1 minus p to the n minus k. So that's for the women. The same thing for the men. M choose r minus k, p to the r minus k, 1 minus p to the m minus r plus k, divided by the probability that x plus y equals to r. And the benefit of it, look at it. So once I do this, all the p is not known to me. I do not know how likely this is to be obtained in the population. The p's and the 1 minus p's completely annihilate, and I have that it's n choose k, m choose r minus k divided by n plus m choose r. I obtain this. So probability that there are going to be k women having the disease, given that x plus y is equal to r, and assuming that there is that men and women are equally likely. Say I'm testing for the null hypothesis, if the disease is more prevalent or less prevalent in women, and the thing is, the overall prevalence of the disease in the population is not known. That also led to assumptions. So far, good.
I have a question.
Go ahead.
Why do you have to do that longer equation first? Why can't you just say that you have the number of women, choose women with the disease, times the number of men and men with the disease, over all of the women and all of the people with the disease?
So
that's
the idea is I suppose that I found with this experiment I found that our individuals are afflicted with the disease, right? So that's what I found. Now I do this, I found it, and then the question is it likely that if I found this result, so I have a bunch of women, a bunch of men, and I found that this is the population that in my sample that has this disease, and I do not know how likely is any individual to have the disease or not have the disease. Yes. So that I do not know what is p. So doing this calculation, I just wonder how likely is it that I would find that k women are sick. I did find that k women are sick, but how likely would I find such a result if there is no difference between men and women?
That's so in this case, the p's happen to cancel out, but they don't always cancel out.
So again, I'm testing the null hypothesis. All I'm saying is, am I expecting to see this disease more prevalent among men or women, right? Or is it equally prevalent among men and women? But I do not know how prevalent it is. I do not know how likely am I to find somebody that's sick. So here I have a sample of some number of women, some number of men. So m men and n women. Yes? Good? So far good. Yes. So understand, right? So if I assume that that each individual is equally likely to have the disease with some probability p, I imagine all the population as just a bunch of trials, women or men, a bunch of trials, and I found that r of the trials were successful. Right, r of the n plus m trials were successful. If it's the same for if the chance of success or finding disease is the same for men and women, it's some unknown p. I do not know how likely it is, right? So I do this procedure and I eliminate the p from the consideration. It eliminates p from the consideration, and then let's say I discover that k women were sick, and then I ask myself, if I discover that k women are sick, was it reasonable? I mean, I could have discovered that amount if or not, if they are equally likely, if the null hypothesis is true. You understand? So if I find that it would be unlikely to discover so many women sick, given that men and women are equally likely to be sick, then I dispense with the hypothesis that they are equally likely to be sick. That's the idea of this thing. All right. I didn't remember this a few seconds ago. You have to forgive me. Hopefully I carry myself well, right? So Fischer exactus. I have no idea what it is, but here it's written. So, right? Good. Makes sense. So then you have this formula. Good. So you see, so this is a hypergeometric distribution. Do you recognize it, right? So we have n plus m trials, right? And we had k from label n and r minus k from label m, right? When you have hypergeometric, you have two labels, and you wonder how many labels do you have, right? So, yeah, you can call it success, failure, right? And the sample, and the sample here is of size r, I guess, right? Size r. So so let's give a concrete example for this test, right? So that we see what we have, right? So suppose that we had a total of 24 individuals, yes? And we were testing for some particular disease, and we found that there were 9 women sick and 1 man sick, for a total of 10 people sick out of the 24. And we had the same total for women and men, 12 women in the trial and 12 men in the trial. We found 3 women not diseased and 11 men not diseased, right? And the question is if the sample was taken randomly, naturally, right? And also just individuals representing the population. Do I believe that this disease afflicts men and women with equal likelihood? That's what this is supposed to do, yes? So let's see. You might kind of already look at it, you think maybe not very much, right? Because look at it, we have only 1 man and 9 women. It seems quite a lot of women have this disease and only 1 man has this disease. Yeah. And so we wonder then how likely it would have been that we would get 9 women sick if the total number of sick individuals were 10 and if men and women were equally likely to be sick. Yes? So then what is it? It is 12 of the women choose 9 and 12 of the men choose 1 for the sick people, divided by 24 choose 10. Yes? And we get that it's 1 out of 1,000. And of course, depending on what's your alpha criterion, if your alpha criterion is 5 out of 1,000, right? So it's less than 5 out of 1,000. That means the null hypothesis may be considered not true. It seems that it's likely that women are far more afflicted, more likely that there is an unevenness in affliction, right? Make sense? The idea. Right. So, and the reason it works is, again, I do not know how prevalent is this disease in the general population. I haven't estimated that. So I try to only judge whether there is, what do you call it, equity or whatever it is, right? Some sort of thing like that.
So does this just calculate like the deviation from what if it were just like equally likely for both?
Yes, how it tries to estimate how likely is it that that both genders in this case are affected by this disease, right? Without bias, right? So also, it doesn't have to be this. You can use it for all sorts of bias measurement. Is there a bias against one category of population as opposed to another population? So that's a pretty interesting thing, right? Especially that people today are super conscious of biases. Good. Right, one population, another population, is there a difference between them? Is one population more afflicted than another? So that's an experiment that tries to predict that without measuring how likely someone is to be afflicted. Good? Okay, so let's go on. Here is a theorem. If x is a binomial random variable with parameters n and p, and y is a binomial with parameters m and p, then the conditional distribution of x, given that x plus y is equal to r, is hypergeometric with parameters n, m, and r. Okay, so here that's kind of a derivation of, in some sense, of the result we had before. So we have two random variables, x and y. So x contains n trials, and they are successful with probability p. Y contains m trials and successful with probability p. And then suppose that we observe that the sum of successes on x and on y is equal to r. Then then the, what do you call it? Then what? The conditional distribution of x is hypergeometric, right? So in other words, you see, there were two experiments, and I only know the combined result of the experiments, right? How many were there successes in the first experiment? It will have a hypergeometric distribution. You understand? So we already proved it. It's we proved it right over here. You see, because what's the conditional distribution? It's x equal to k given this information, and we know that's a hypergeometric distribution. That's even clear intuitively. I hope it's clear intuitively, because you see there is no bias on where successes occurred, right? Either in this region or in this region, right? There is no bias over which individual trial it occurred, to be precise. Of course, there might be, if one experiment was longer, more successes will be in the longer experiment, but there is no bias in the individual trial, right? So if we had r trials, r is equally likely to be distributed among any of the r successful trials among any of the n plus m available trials, and that would have a hypergeometric distribution. Make sense? Yes, confirm, guys, that I'm talking there and it makes sense to you, all right? So right, yes or something.
So it doesn't confirm that there is a bias, just how likely that bias is to occur if that were the statistic.
Yes. Well, how likely is the observation to occur if there is no bias? So you understand what can you do? The best you can do is this. If something is very unlikely, you don't believe that you witnessed it, right? It's like when you go and say, I found this woman and she is a diamond among people, right? So then you don't believe the person because many people say that, and it's very rarely true. It's very rarely that you find a diamond. Yes. So that's the idea here as well. So if I found that that this observation was very rare, I start thinking that this observation was the assumptions of this observation are not correct. That I observed something not real, not true, right? So in this case, you see, under the assumption that there is no preference to the gender, I observed an unlikely event. And what's unlikely? That depends on your definition, right? Maybe 1 out of 1,000 is not that terribly unlikely, but unlikely. Right? If it's 1 over a million, it's even more unlikely. If it's 1 over a trillion, it's extremely unlikely. You don't believe it at all. So that's the thing, right? You might be mistaken, but you're mistaken only 1 out of 1,000 times that you are that this is not, yeah. In saying that that there is no that the null hypothesis is true, you will be mistaken only once every 1,000 of such observations. Or such judgment calls, to be precise. You understand me, guys? All right, if x is hypergeometric with parameters w, b, and n, so w is a label and b is another label, right? White, black, white ball, black ball, and altogether we have a sample of size n. Then, of course, if the number of white plus black balls is going to infinity, if it's very large, where the ratio of white to total remains the same, and then in the limit it will converge to a binomial distribution n and p, where p is this thing. You understand? So if I increase the balls basically I increase the number of balls, and by proportionality, I keep the same ratio of white to total. And then the hypergeometric transforms into a binomial formula. That's pretty obvious as well, right? Because remember what makes a hypergeometric not binomial is that once you sample something out, you don't replace it. But if you have if the population is big, then removing something is a very small, it has a very small effect. Yeah. So probability that x equal to k, what is that? And here guys, be careful. Let's see if you recall it. It's w choose k, b choose n minus k over w plus b choose n. That is a binomial. That's a hypergeometric, right? And that's where I assume that that the sample is random, but the labels white and black is not random, right? So I imagine the balls. I see them first colored, which is white, which is black. W are colored white, B are colored black, and I choose a random sample. And there is a symmetry here where I can imagine choosing a non-random sample and randomly labeling W balls white and B balls black. You understand? So I first sample non-randomly. When I sample, they are gray. It's like fruit, and then they all mature and they have some sort of entanglement. So exactly W altogether in my entire population will become white, and B altogether in my entire population will become black. Okay, so you see the formulas here. So then this is the same. W choose k, B choose n minus k divided by W plus B choose n is the same as n choose k, right? Because I'm gonna have n of my sampled balls become white. That's what the n choose k represents. N choose k, and here I will have W plus B minus n is the remaining balls. Out of the remaining balls, W minus k will become white, right? I'm only focusing here on what becomes white. So exactly W becomes white. In my sample, K became white. That means in my non-sample, W minus K will become white. Are you with me? Confirm in the message, guys. This is very difficult, I believe. Right, so good. All right, and then in general, why do I divide by W plus B choose W? Because any of the balls are likely to become W. Just pick any group of W's, and they're equally likely to be the ones that become white. Good. And then I just carry out a bunch of calculations. So I expand this, n choose k I keep. You see the n choose k is the n choose k of the binomial distribution, as you can imagine. We have n trials here, right? And then whatever else, I just do a bunch of algebra. You see, we have, this is the algebra. And then once you expand it, you take the limit as n goes to infinity, and you will get this binomial distribution. Just think about it, right? Expand it, and here it is, expanded. Simplify it out. N is equal to, if you remember, n is W plus B, right? N is W plus B. And n is large, so it's large. And the limit, what you end up having is, you see the denominator just becomes 1, and here you see the probability, right? So n is becoming large, k is keeping a particular ratio to it. Okay. And again, this calculation, you should have anticipated it to be true to begin with, right? So why? Because all this is saying is that if we have a very, very large population of white and black balls, then picking just and k is small, right? K is like just no, sorry, n is small, right? The sample is small, then I'm not removing too many whites or blacks to alter the ratio for the next picking, right? So first, if I had a success, I removed one white ball. The total ratio of white balls to all balls remains more or less the same. Very, very slightly affected. That makes sense, yes, guys? If the population is very large, you would not notice the effect whatsoever. It would be like binomial. All right, good. Now let's talk about another distribution, geometric and negative binomial random variables. So a sequence of independent Bernoulli trials is run until a first success occurs. Each trial has probability of success P. So they're independent, but I run the trials, not n trials, I just run them until I have my first success. Make sense? So if the first success occurs right away, I stop. If the first success occurs on the nth trial, I stop on the nth trial. So let x be the number of failures before the first success. Then x has a geometric distribution with parameter p. So for example, suppose I have k failures. K could be 0 failures. In other words, first trial was a success, or 1, or 2, or 3, or 4. Or in general, suppose I have k failures. Probability of failure is 1 minus p. So it will be 1 minus p to the power of k. And first success is the last trial, the k plus 1th trial. Good? Clearly, this is a geometric series, and its summation will equal to 1. So with probability 1, x will equal to either 0, or 1, or 2, or 3, or some finite number. If x is geometric random variable with parameter p, the cumulative distribution of x is given by this formula: 1 minus 1 minus p to the power of, this is the floor function of x plus 1. Okay, now why is that the case? That's pretty simple. What is the cumulative distribution? It's just the probability that x is less than or equal to little x, to some particular number. But x can only take integers. If it's less than or equal to x, it must be already less than or equal to the floor, right? So in other words, if x is 1.3, then x can only be equal to an integer, right? So that means x has to be less than or equal to 1. That's why I can take the floor here. Clear? Now the probability that x is less than or equal to the floor is 1 minus the probability x is bigger than the floor, which is the same as 1 minus the probability that x is bigger than or equal to the floor plus 1. Because if x is bigger than the floor is an integer. The next integer you can take is the integer plus 1. So you see, if I say 1 minus this inequality, I can make it less than or equal if I add 1. Everybody understands this step? That's only because x only takes integers, right? It's 0, 1, 2, 3, 4, 5. This is some integer. If I'm asking for the probability that x is bigger than the integer, that's the same as asking the probability x is bigger than or equal to the integer plus 1. Because I can only take integers. Right? If I'm bigger than 1, I must be bigger than or equal to 2. Yes? So what is this? It's 1 minus probability that x, floor x plus 1 failures at least. Right? So that means it's 1 minus 1 minus p to this power, because I have those many failures. You can also think of it as summing the geometric from a particular value onwards. Okay, there are many ways to solve it. 1 minus, I mean, you see, don't look too much about what is written here. You can figure it out on your own. Simply, it's easiest, I think, to, well, you can think what you prefer. You can actually do it in one way or another, right? It's very easy to sum. Either you sum up to a finite number, or you take 1 minus the summation from some number onwards, and you have a geometric series that you know how to solve. Am I right? Right? You don't need a review of that. You already know it, right? We reviewed geometric series. You understand what I mean, right? So you can figure that out. So figuring out this function is nothing so interesting and special. So let's now calculate expected value and variance of this random variable. So the expected value, it's simply k multiplied by x to the power of k. Right? I need this x is now the probability, right? It's really I'm adding up only this part without multiplying by p, right? Just something to the power of k. So I need to know what is the summation from k0 to infinity, kx to the k. Now what can I do? I can create a recursion. I can write it as the summation where k goes, because it's 0, I can update it to go to 1. 0 is not important, right? K equal 1 to infinity, k minus 1 x to the k plus summation x to the k. You see what I did? I split k into k minus 1 plus 1 and distributed the x to the k. You all see that? If you are stuck or confused, you let me know now, please. Okay, nobody confused? Wonderful. You understand how I do it. And so what I can do here I can factor out an x, and I have k minus 1, x to the k minus 1. Then readjusting, this is the original summation e. So this is just equal to x times e. You see that? By factoring an x, it's again, I start from 0, then 1, then 2. That's all that matters. So it's x times e plus, this is just a geometric series that equals to x over 1 minus x. So I have e equal to x times e plus x over 1 minus x. When I simplify this equation, e equal to this, I simplify, I get that e is equal to x over 1 minus x squared, right? And therefore the expected value of x is this summation k times 1 minus p to the k times p, which according, if I just factor out the p and sum everything else, it's 1, so x is 1 minus p. So 1 minus 1 minus p is p here. It's p squared, and here it's 1 minus p. And here I just multiply by p, and I get 1 minus p divided by p. Clear? Just calculation here. Now we can do the same for the variance. To compute the variance, I will need to know what's the expected value of x squared. Good. The expected value of x squared is k squared times 1 minus p to the k times p. And look what I do. I do the same thing. I split k into k minus 1 plus 1. And because it's squared, I use the quadratic formula. It's k minus 1 squared, 2 times k minus 1, and 1 squared last. You see this? And p was factored out. It's just quadratic formula and distribution of summation through the quadratic formula. Good? So what do we get? We get 1 minus p. So once I look through it, I get, what is this thing, right? I get 1 minus p, the expected value of x squared. The reason is that, you see, just if you distribute it over here, it becomes, if I factor 1 minus p, it looks exactly like the original summation. So it's 1 minus p expected value of x squared plus 2, 1 minus p, the expected value of x, which we already know, plus the summation, which is 1 minus p. Okay, the summation times p is when I factor 1 minus p, it's what survives. It's p times this, and factor out 1 minus p becomes 1 multiplied by 1 minus p. Everybody understands this line? Especially, guys, see what you should worry about. Do you understand the idea? The idea is I just try to see the formula within itself. So the expected value of x squared, once simplified, it's simply 2 times 1 minus p over p squared plus 1 minus p over p. And variance it's the expected value of x squared minus the expected value squared, and simplifying, I just get 1 minus p over p squared. That's the variance. Make sure you can calculate it. You don't you can calculate it, yes, on your own. Some of you, let's see, let's look at faces. Well, most faces I cannot see. The faces I see seem like they understand more or less. So if something happens, you let me know, yeah? I worry that I'm just saying p, 1 minus p multiplied by 1 minus p times p divided by p, right? And amplify by 1 minus p plus p, right? And that's what you're hearing, right? You're hearing more than that, or at least you can ignore everything I'm saying, but you can derive it on your own without much problem. Am I right? I'm not just saying p 1 minus p squared, right? You're understanding. Confirm, right? Yes. Right, you can ignore the entire dribble, right? The idea, you have it. So if you close this, you leave this classroom, you can derive it. Correct? Okay, let's hope so. If not, you can stay after class. We can do the calculation together, or try the calculation first and let me know that you can carry it on your own. Yeah, okay, so negative binomial distribution. I never remember the names, right? Geometric, I can kind of remember, but negative geometric. Negative binomial. So here it is. In a sequence of independent Bernoulli trials with success probability p, let x be the number of failures before the R of success. Okay, so we have independent trials, and we want to know how many failures occur before we get the last success. So the probability that x equal to n, right? So you understand this, yes, guys? So what am I saying? So we are going to continue sampling, performing more trials. We perform 1 trial, 2 trials, 3 trials. We're going to perform the trials until we generate exactly R successes. It's kind of like binomial, except the number of trials isn't fixed. We have to perform at least R trials to achieve R successes. Correct? Right, and x counts how many failures occurred. So what can x be equal to? All right, x counts the number of failures before that happened, right? So x can equal to 0, or to 1, or to 2, or in general to n. Yes, in general it can equal to n. All right. So what's the probability of having n failures? So that means that we had how many? We had n failures plus R successes, correct? So altogether we had how many trials? We had n plus R trials. Do you agree? If I had n failures, I must have had R successes, n plus R trials. The last trial must have resulted in a success because I stopped, right? So then out of n plus R minus 1, I can choose where to place the remaining R minus 1 successes, right? So I have n plus R minus 1, total failures plus total success is minus 1, right? Why minus 1? Because the very last trial was a success, the R success, and everything before was either failure or success with R minus 1 successes. So I take n plus R minus 1, choose R minus 1.
So we can have like multiple successes within the trials, but the last one has to be a success.
The last one has to be success, and multiple meaning we have exactly R, to be precise, not just multiple. We are stopping as soon as I reach, let's say, 5 successes, right? You are going to continue performing trials until you have 5 successes, right? So you perform 5 successes plus the number of failures. So let's say maybe you only had 2 failures, then you performed 6. Sorry, if you have 5 successes and 2 failures, you performed 7 trials, right? And out of the 6 trials before the very last trial that resulted in the success, you gathered exactly 4 successes. Clear?
Yes.
Wonderful. It's amazing that honestly I am in awe before your ability to listen to me and understand anything. It's very impressive. Good work. If you understand, right? I think all I hear when I speak myself, I hear P, success, failure. Good. I cannot listen, or. So here what we have is this situation. You understood the explanation, yes? Now let's see how good you are at calculating expected value. But what's the expected value of X, where X is the number of failures? How many failures will we have? On average. Let's see if you can do that.
Sorry, can you repeat the question?
The question is, if I perform this procedure multiple times, on average, how many failures will I find? In other words, what is the expected value of failures for independent trials with probability P of success, where I have to gather R successes? Question clear? Hmm. Oh, by the way, for all your rodents out there, you know, the exam, you can submit it still. Let me know when you're ready, please. Here is a hint if you are stuck. Imagine the easiest way to do is sum, right? The expected value of a sum of random variables is always the sum of the expected values. So you might imagine how many failures were before the first success, between first and second, between second and third, and between r minus 1th and rth success. I'll help you in a moment, yes? All right, I think let's do it together, right? Ready? So here is the idea. Again, we have x1 plus x2 all the way to plus xr, where xk is the number of failures between k minus 1 and k success. X1 is, of course, before the first success, yes? And xr is before the r success. Now think about it. Those things are, how are they distributed? The successes are independent, and each of them is geometric, it has a geometric distribution. Think about it. This is how many failures before a success. The next one, again, you restart it. How many failures before success? Do you see that? Between two successes, the random variable between them, because there is no memory of what happened before, it's independent. It's just a number of successes, so number of failures before next success. So it has a geometric distribution, and we know that the expected value of the sum is the sum of the expected values, each of them individually distributed identically, and has expected value 1 minus p over p, which is the expected number of failures for a geometric random variable. Yes? Are you with me? Now, can you calculate variance? You have the variance of geometric right over here. Right? 1 minus p over p squared is the variance of a geometric if you need it. So the next question is, what's the variance of negative binomial distribution? Okay, interesting. Let's see it together. We have already 2 people answered it. I just want to move. So again, guys, x1, x2, all the way to xr are independent. Yes? And so variance of sum is the sum of variances. I hope you remember that. And simply it is r multiplied by 1 minus p over p squared, very quick, right? Because the variance of each of them is the variance of the corresponding geometric random variable. Here is a question. There are n types of toys in a cereal, inside cereal boxes. When you buy the box, any of the n types is equally likely to be in this box. How many boxes do you need to buy on average to get the full set of n toys? All right, what is happening, guys? Are you close to the solution? All right, let's do it together. Okay, Naomi. Nice. So here is how we can approach it. So X, number of cereal boxes bought to gather all toys. So we have X1 is the number I need to obtain first toy. X2, the number I need to obtain next new toy. All right, so and onwards. Xn is the amount of cereal boxes I buy to obtain the last toy. Now, what is the probability that xk equals to j? You understand? So think about it. Xk equals to j means that at the xk stage, the toys that I gather, I haven't gathered the kth toy, and I'm equally likely at each trial to gather any of the toys, right? So I have a particular k-1 toys that I already have, right? And out of n. So this is the probability I will not gather a new toy, and this is the probability that I will gather a new toy. So if x equal to j, there are j-1 trials where I did not gather a new toy, and then I gather the new one. Okay, that's the probability, and the expected value of x sub k is just a particular geometric random variable, which we know equals to, in general, 1 minus p over p. Right, that's the expected, and then the p is what? P is this thing, and that's 1 minus p. Yes. So altogether, we obtain the expected value is the expected value of each of those individuals, and that's n divided by n minus k plus 1, as Naomi said. So it's n multiplied by 1 over n plus 1 over n minus 1 all the way to 1. Okay. In other words, this is the trial where I obtain. I need to obtain only one toy. First, even to obtain just a new toy, if I just buy a cereal, I'll get it, right? So that's the expected value. So for instance, if there are 5 toy types, the average number of cereal boxes is 5 multiplied by this summation, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, which is about 11.4 boxes that I'll need to buy to obtain all the toys. Good? So everybody understands how I made the calculation, guys? I mean, even if you haven't carried it through, do you understand the idea? So I just sum the expected values, but they're not the same. X1, it's pretty easy. X1 is going to be 1 box, right? To get the first new toy, it's 1. But in general, what's the expected value of xk? It means that I gathered already k-1 toys, and I want to gather the next new toy. So the expected value is just how many do I go? Do I need to buy 0 boxes or 1 box? I mean, right? 0 obviously not, right? So 1, 2, 3, 4. How many boxes do I buy to get the next new toy? And it will have a geometric distribution, just different from the one before, right? X1 will have a different geometric distribution from X2, from X3, and onwards, right? So those are just the sums for the different geometric distributions. Clear? Naomi solved it correctly. I haven't seen other solutions, but for the rest of you, is it clear? Yeah, confirm, guys, right? Or you want more explanation? We only have, what, 4 minutes? I do not know what I can do with 4 minutes, not too much. Maybe I should extend it to 10. Do I have time to introduce this thing?
So, Professor?
Yes.
So we're going between each of the successes in order to determine the average number of those, and then going from that, or
so the way I set it up is that the total number of boxes needed to obtain is the boxes before and including first success, the boxes from first success to the next one, where success is when I get something new. Okay.
okay.
And then on all the way until I get to n. So or whatever, how many toys I forgot I had. I said n, right? n, right? So they're going to be x1 plus x2 plus xn. Because I know expected, doesn't matter independent or not, right? Expected value is always, expected value of sum is always sum of expected values, which I use to my advantage. That's always true. We
Okay.
verified it, right? So all I have to do is calculate the expected value of some arbitrary expected value xk. Okay, so I have only 2 minutes, guys. I wonder what to do with 2 minutes. Do you want to see what a German policeman sent me the other day? I can show you that. He was on a mission suppressing civil rights somewhere. I can show you what he was doing. No? All right. I don't know, what can I do then? Should we spend 5 minutes and talk about negative hypergeometric random variables? Can we see it? One person wants to see it. You don't look that excited. Okay, so I'll stop the recording. I'll show you the German message. You try to figure out what they were suppressing, okay? So